Okay. Any additional homework questions you guys want to take a look at?
21.
21. That was the one. Okay.
You would here or here?
All right. Analyze a trace when the surface that is intersected by the planes.
I'll put it here for now.
Find the coordinates of the focus of the parabola. Okay. Yeah. Actually, I want to get to this stuff. Let's, instead of going through all of it, we're just going to do the cheater's way and look at what the book does, and I'll explain it. Okay, so here for number 21, here is the work that the book has for there. So in general, if we're asked to find a trace for different planes, we kind of did this a little bit when we worked through example 13 yesterday, where we said since this thing has been centered around different points, instead of looking at the x, y trace and things like that, we kind of change it to a different trace there. And that's some of the idea that's going on here. So we have this surface, and just from looking at the equation, we can hopefully tell this is going to be a paraboloid since we got an x squared and a y squared, but not z squared. We know we're going to have a paraboloid there, which kind of follows up with questions A and B there. So anyway, if you're graphing your calculator or graphing technology, you're going to see this paraboloid. It's going to kind of open up along that z-axis there. And so if we think about the plane when y equals 5, that plane is going to be like going up and down. It's just going to cut like a little slice off of the side of that whole entire cone there, which makes a parabola. Okay? And then so if we go in the x direction, it's just going to cut it perpendicular to that, but it's still going to make like a little slice of that parabola there. So in order to go through and find the coordinates, like it's asking about here, we need to know the equation of those parabolas, and then remember how to go back and find focus and stuff like that there. So that's what's going on here. There's their equation. They went through and said, okay, for part A, when y equals 5, just plug a 5 into the equation. You're going to get out the equation of parabolas. So z equals x squared over 2 plus 25 over 4. And then that thing below that, they're putting the parabola in that more standard form that we had from Calc 2. Let me see if I can quickly pull up my Calc 2 notes. Yeah, okay, so here's some Calc 2 stuff. Oh, I don't remember stuff off the top of my head there. You know it when you're teaching it, but then once you do it, okay, it's low. So if that loads, back in Calc 2, we had that general equation for working at parabolas, and from that we could easily find what the focus was and the directrix and stuff like that there. And so that's what I was going to try to go through and pull up here. But I'm freaking out that instead. Yeah, so this will work here. Okay, so when we're working with a parabola, there we go. Okay, so we're looking for an equation that looks something more like what we have here. Okay, that lower set, those conic forms there. So in those conic sections there, depending on what h is, what k is, what p is, we can go through and find the focus, find the directrix and stuff like that. Does that sound familiar? Okay, whether you remember how to do it off the top of your head or to go back and look it up, but that's what it's looking for there. And so in the book's work here, this second line that has a 2 equals all that stuff there, it's going back and finding it in that structure, and then from that version of the equation, we can go back and find out what the focus is. Okay, so I say go back and check your notes there. X equals 0 is coming from the subtracting nothing over here. Y equals 5 is coming from the fact that we forced y to equal 5. And then this is really just the shift we're doing in the z direction. Okay, and then all the same exact things, but for when x equals 4. We're going to do the same thing, go back to your original equation. Let x equal 4, you're going to be able to simplify that down. You're going to get that general equation for a parabola. And then same exact idea as that. Similar idea there. We're forced x to be 4, y has no shift, and I'm not sure why they have z equals 9 instead of 8. No, because this isn't 6 2/5. That'd be 25/4. So what am I missing? My notes never been good. Freak that program out. Blah, 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 blah. I wish it was my notes instead of this. 4p is just the same thing. Okay, vertex in the parabola of the equation. Focus. This 7. It's not just a shift, so I don't recall. If my notes were open, I could find it easily, but I can't think off the top of my head there. So my suggestion would be go back to your notes from Calc 2. Hopefully you have them somewhere, or ask the internet. but I know that from this equation, I just don't remember what the formula is. I think it has to do with the 4 times p up front. You have to do some work with that. But from that equation, I know that's where that focus comes from there. So it doesn't really answer the question, but hopefully it helps a little bit. Happy to do that. If over the weekend it still doesn't make sense, send me an email, or also on Tuesday if you want to have class on Monday. Ask on Tuesday. You can go back and this, so I can give points back for it. Okay, but try it on your own. Maybe that gives enough to answer kind of some questions there. But yeah, that general equation is what they're using that to come up there.
I was having trouble with 19.
Find the equation of a source of revolution formed by revolving the indicated plane around the given axis. Okay, so we're taking the equation z equals natural log of y, and we're going to rotate it about the z-axis. So since we're rotating about the z-axis, and I'm just going to leave the answer here instead of changing it. That's why on this left-hand side we just have x squared and y squared because we're missing the verb we're rotating about. And then on the other side, where does all that stuff come from? Well, since we're rotating with the z-axis, the generating function has to be in terms of z. And so if we go back and solve that equation for z by using the exponentials, you just square it, and that's where the 2x comes from, but that's where it goes up and does that. So whatever axis you're rotating about, you're going to have the other 2 variables squared equals, and then that would be the right-hand side of the equation is going to be in terms of that same variable you're rotating about.
Oh, I see. I was just writing I was getting that answer by writing notation on. I was writing D, Z.
Oh, I see. I'm surprised it didn't count that because it usually is pretty good about that. But yeah, that what you have is okay. Just write this 2D instead.
Okay.
Yeah, it's usually, I'm surprised. Like I said, I'm surprised you didn't catch that. It's usually pretty good about counting things like that. So, that's programming this one. Anything else?
Oh, does the coordinate plane matter there when it gives that?
Number 10. Number 10, I don't know what, but
Number 10, the coordinate plane doesn't matter on this one, no. Okay, number 10, you say, Edwin?
yeah, number 10, I'm getting it wrong. I don't know why. I don't know if my algebra is wrong. But
Okay.
I did a cross product and I had an equation, but they told me it's still wrong.
This is the one you sent me a picture of, isn't it?
Yeah.
I just remember you said that. I never replied back. I will take a look at your picture and I'll see if I can figure out what's going on there. I'm sorry. I read the email and then it got left. So I'll look at that after class. I'll take a look at it and get back to you on that one.
Okay, thank you.
Okay. Good to start. Next section. And if you have questions over the weekend, go ahead and send me an email. I've got WebAssign set up now where hopefully it sends me an email if you ask a question within there. If that helps. All right, but this is still not responding.
Has the homework thing been resolved with the access code?
So is yours still not working, Cole?
No.
Because on my end it shows you're registered, which is weird. So that would mean that whatever code you entered, it should work there. You still have the temporary access bar on top?
Yeah, so here, let me refresh it real quick.
Okay.
Mine's not working either. Oh, you have to show.
Caleb's isn't working? Yeah, and then I also have that Brian's and Murillo's aren't working either, right?
Nope.
So Edwin's the only one that's okay?
So far,
Well, that's less than ideal.
I don't see anything.
Mine said I have 5
I
days.
couldn't find Lucy yesterday. I tried to find her, but I couldn't. Okay, sorry, Cole, go ahead.
It says I have 5 days left in my subscription.
Okay. We are having problems on this end with some of that stuff too, so I'll try to find Lisa today. I couldn't find her yesterday. She's just super busy, so I'll try to get a hold of her today. At least we've got 5 days. You can finish this homework, and then we'll get it taken care of before it gets too much of a problem.
I'm almost done. I have like 1 problem left.
Okay.
I've introduced so many times, but you
All right, let's start 11.7. So if you like polar coordinates, you'll like this section. If you didn't like polar coordinates, hopefully we can change your mind since you like them, since you like this section here, okay? We're going to talk about basically the 3-dimensional version of polar coordinates and then a different coordinate system, so a third coordinate system called spherical coordinates there. They are both very useful in the right situations, okay? Especially the polar coordinates or cylindrical coordinates, what we call them in 3 dimensions there. They make some problems so much simpler, okay? So if you didn't like them before, then I apologize because they're not going to go away. They actually turn out to be incredibly handy and incredibly useful to work with there. So hopefully, as we work with them some more, you remember them and they're not so bad. So before we even get to that stuff, though, graphing things, we know how to graph some simple stuff. So for example, graph the function 3x minus 1. What's the graph going to look like?
3 on the x and y.
Yeah, it's just going to be a line with a slope of 3 and a y-intercept of -1 there. So we're good at graphing this. Y-intercept first, up 3 over 1, and we've got that. Okay. Oh, the line isn't drawn very nicely. Now, the good thing about stuff like this is when you know what the graph should look like based on the equation, it makes it a lot more, you might even have to graph it depending on what you're doing with it, but it makes it much quicker to kind of graph it and know you're doing it correctly there. And that's kind of the same idea as you progress through anything. I mean, we can graph parabolas and trig functions and all that stuff too on that 2D system there. So hopefully the understandings of that kind of carry through here. In Calc 2, we then talk about parametric equations. So example 2 goes through and does a parametric equation. The benefit of working at parametric equations is we have like additional information here. If we often think about that new parameter t like time, then we're saying, okay, well, instead of just knowing one change, like how far it's gone over time, this allows us to say, okay, well, where is the location of it? So what's the x value, the horizontal component? What's the y value, the vertical component? We can kind of track the object's path instead of just how far it's gone. So yes, our calculator can do this, but kind of the real long way of going through and graphing is we can pick some points. And the nice thing about this too is if we kind of stick in order and make t get progressively larger, we can kind of track the path here. So let's just pick a few points. So -2, -1, 0, 1, and 2. If you plug in -2 in for x, -2 squared is +4. Plug in -2 for y, -2 over +2 is -1. And that 4, -1 gives us one of our points. So 1, 2, 3, 4, -1.
I don't know what it's
And we can continue doing that with the rest of the points, just going back and substituting into x, substituting into y. And eventually we'll get a fairly good idea of what the path is at this thing, whatever this is in this case, that this object is tracking. 2 squared is 4. So if I graph the rest of those points, 1, -1/2, 0s. Depending on how picky your Calc 2 teacher was, maybe you'll just draw one arrow, maybe you'll draw multiple arrows. But the idea is that this is kind of showing us a path that something is traveling on here. Okay. That idea of working at parametric equations is a lot of what we're going to talk about in the next chapter. So the next chapter talks about vector valued functions, but it basically says, okay, this idea, but in 3 dimensions. So instead of just tracking the path on that plane, now we can track the path through space. Maybe we can make spirals or we can make sorts of curves and things like that there. So this idea we're going to spend a lot of time with in the next chapter. Okay, chapter 12 is heavy on basically parametric 3D functions there. Okay. But still, that was working in 2D, nice flat surfaces. We also talk about graphing with polar coordinates in 2-dimensional space here. And maybe you remember what shape this makes, maybe not. I'm not going to go through and worry about sitting there picking points to plot this one. We could do the same thing. We can go through and pick points to graph this one with. But if what do I want to graph it with? Let's use Desmos. We graph that guy in Desmos. Is anyone real comfortable at polar coordinates? Remember what that's going to look like? Oops. Not quite a circle on the x-axis, but it's a good guess. If we didn't have that 3 in front of the theta, then yes, we'd have a circle.
It would be like a spiral.
No, even more fun than a spiral. Thirda. Okay, this is one of those rose curves. Okay, and I don't expect you guys to remember that stuff there. That's not something that's going to be super important for us. But just know that calculators can do this, Desmos can do this. Definitely not a function. In rectangular coordinates, that thing is miserable to try to have an equation for. But in polar coordinates, it's super simple. It's easy to integrate, it's easy to derive. There's really not a whole lot of challenge in working with this equation here, which is why we bother working with these equations. Okay. And if you do recall, when we go back and change these things here, so what A represents is the radius of this. So we can make this guy bigger or smaller. And then what that 3 represents is how many petals we have. It's related back to that. Oh, change that to something more interesting. So depending on what that number is, we're going to have different petals, numbers of petals there. Okay. Yeah, something like that. Yeah, so there when it's 2, we actually have 4 of them. Little things like that, honestly, I didn't require students to know, but there you go. All that kind of stuff there. So we know how to go through and graph these. So for that shape that we were actually working with, B was 3, A was 2. So there was the graph you can sketch in your notes there. 1 petal on the x-axis, and the other 2 petals off to the sides. And with a radius of 2. So kind of like this. Petals are a little funky, but we get the idea.
It enhances the features, but
should review a tad more here. I have this in the notes in a minute there. What does R represent in polar coordinates? So the distance from the center there. Can R be something negative?
No.
Yeah, it could still be something negative there. If we've got a negative radius, we're basically going to go backwards there. So like if we were graphing points, so say we had the point we wanted to graph that was like -2 pi over 4. Oh, let's make it a bigger number. I'll say like -4, just so it doesn't bunch up in my graph there. Okay, well, pi over 4 we know is going to be this line right here. If our radius is -4, that means instead of going in the positive direction, we're going to go backwards 4 units. So that would be a-okay to have a negative radius. Okay. Remember, the other thing with polar coordinates is there's a lot of ways we can write this point. I mean, that's just one way I can express this point. If I did want it to be a +4, then that's the same thing as angle pi over 4, 4 pi over 4, 5 pi over 4. Or yeah, or -3 pi over 4 we can go back and use. So there's an infinite amount of ways we can express these angles there. Those same things are going to happen in 3 dimensions. Okay, so we usually stick with positive values for R, but it could be something negative. That's okay to have negative values for R there. Okay, and then theta, hopefully remember, is the distance from that positive x-axis. So the traditional kind of trig angle we measure is what theta represents there. All right, then we get to talk about 3-dimensional shapes. So how do we know, or back up a little bit, what shape is this going to give us in 3 dimensions? What kind of surface is a better word for it? It's a plane. How do we know it's a plane?
Because it has 3 variables.
Yeah, because it has 3 variables. That's important, and they're all just linear. Just raise the first power there. Okay, so we're working with a nice plane. We can go back and sketch this, which won't take too much time. So let's review that. Remember the way we talked about sketching planes is we said, well, let's use the traces. So if x equals 0, we'll get an equation. If y equals 0, we'll get an equation. And if z equals 0. And those kind of give us an idea of where this intersects the main axes. It's kind of hard to see. I'll go back to coloring black. So if x equals 0, we've got 2 times 0, which is a 0. So -y plus 3z equals 4. When x equals 0, it means we're kind of on this plane right here. If you can imagine that that's the plane that we're drawing on. So graph that guy. What's that going to look like? Oh, I need one that has to go the other direction. I should have picked better numbers. We're going to need to go the negative direction for this one too. So if y is a -4, z would be 0. And if z was 4/3, y could be 0. So somewhere around here. If we try when y equals 0, we'll have 2x plus or minus 0 plus 3z equals 4. So still, if z equals 4/3, we get 0, which makes sense. But now if x equals +2, we'll also get another point. And then the last one we can go back and check, but it's just going to cross through right here. Okay, so this plane's kind of sitting in that backwards quadrant where some things are negative there, but we can go through and sketch a plane. If you want to do this on your calculator, go ahead and get z by itself. So minus the 2x minus or plus y and divide by 3, and you can graph this to your calculator. Okay, your calculator is not too difficult to work this one. Okay, so going back to what we're actually talking about in this section is here. Well, now how we get more complicated surfaces, or how there are some other ways we can go through and graph in the 3-dimensional system there. We did talk about lots of other types of surfaces. We can have cylindrical surfaces and quadratic surfaces and surfaces of rotation. But some of those will kind of show up as we talk throughout this stuff here. Okay, so cylindrical coordinates are just the 3-dimensional version of polar coordinates. We're still going to have r, we're still going to have theta, and really all we're going to do is just introduce z to this. We're not really going to change things a whole lot. So I'm going to go through and review some stuff and hopefully do some calc that looks familiar there. But that's because really all cylindrical coordinates do is just the same exact thing as polar coordinates there. So I want to make sure everyone remembers how to work with polar coordinates. Okay. So polar coordinates, like we said, they take r and they take theta. R is talking about that directed distance from the origin, and theta is talking about some kind of angle. Does anyone remember how we convert between rectangular and polar?
R equals something that.
I hear different parts from different people. Yes.
R cosine.
Yeah, we remember that. So that means y equals r sine theta. And that comes directly from trig. Okay, I mean, that is just taking a trig identity and just rewriting it a little bit there. When we connect from the rectangular to polar, we can also express this as like using circles. So x squared plus y squared equals r squared, or tangents. And again, those are just coming directly from trig or from working with circles there, but we've got these two kind of ways we can think about how these guys are connected there. If we're given a point in polar coordinates, we can convert that to a point in rectangular and vice versa. If we're given an equation, like we'll do in just a minute here, if we're given an equation of one, we can convert to the other. There are some short ways you can do this sometimes. If you notice things, remember trig identities, but there's always kind of a long way we can go back and do this here, and we'll talk about both real quickly. So for example, if we've got this equation, y squared equals 3y minus x squared, okay? And just because I like Desmos and we don't get a chance to graph things in 2 dimensions very much, let's graph that guy. What's the graph of this going to look like before I type it up? Can anyone tell me?
Is it a parabola?
Yeah, it's going to be a circle. Oh, because it's shifted center. It would be a parabola if we were missing a squared on the other one, but since we've got both of them being squared, it's a circle with its center having been shifted. Again, I don't expect you guys to know it from looking at it, but if you do remember, wonderful. So anyway, there's our equation. Okay, it's not a super difficult equation. It's not really that difficult to work with the rectangular coordinates either, but that's what we're going to go through and convert to polar coordinates. So since this is review, does anyone remember what we could do to convert this to polar coordinates? We wanted to get in terms of r and theta. Yeah.
3r sine theta.
Yeah, so kind of if nothing else, we can go back and we can take this information and we can plug it in to the other equation there and then just do a bunch of math. And that's a fine way to do it. There's nothing wrong with doing it that way. That way will always work. So since we just said y was r sine of theta, we'll have r sine of theta squared equals 3 times r sine theta minus r cosine theta squared. And if you're thinking in the back of your head, there's probably an easier way to do this. You're right. We'll talk about it in just a minute. Let's finish this. So go ahead and clean that up a little. R squared sine squared theta equals 3r sine theta minus r squared cosine squared theta. What can I do with that?
Sine squared theta. Can you change the sine squared theta and factor out r?
Yeah, so we've got an r as a factor in all of these, right? And I heard that a few times. We can definitely factor out an r or just divide through by r, however you want to think about it here. If we imagine dividing everything through by r, we've got to be careful. What happens if r equals 0? Is this step possible if r equals 0? No. So, and this will show up a few times in the section we're going to work with. When we're simplifying these equations, it's very common to do this. And even if you think about factoring, at some point you're going to end up dividing by r. And that's okay. So when you divide by a variable, we have to make sure we go back in the end and check our work. If that variable can equal 0, we're going to lose that solution when we do this step here because we can't do it mathematically. So we have to check our end equation to make sure it still works. So we will come back. We're going to check this at the end and hope it'll make more sense what I mean there. Okay, but we can divide through by r. That is okay. We're left with r sine squared theta equals 3 sine theta minus r cosine squared theta. Okay. Let's add that cosine squared theta term to both sides. So hopefully everyone can see the best trig identity in the world happening over here. Okay, what happens on that left-hand side?
That's what Brad used to say. It becomes r. It becomes 1.
It becomes r times 1. Yay, okay, that's the best thing ever. I love that identity. So we just get r. I'll write it out here, but hopefully we're all familiar with this identity. Okay, sine squared theta plus cosine squared theta just equals 1. R times 1 is just r, and that is where we go. That is what we're looking for right there.
So I can now see the other way around. Can we do that with the original equation?
Mm-hmm. Okay. Mm-hmm. If we add x squared to both sides? Yep, we'll do that in just a second. Okay, like I said though, since we did divide by r, we divided by a variable, we have to go through and make sure that we didn't lose that solution. Because if r equals 0, that step up here, then it breaks the whole equation. And so essentially what we're doing is, okay, well, if r equals 0, we'll check that later. Let's go through and just do the rest of this here. So we basically have to check and see, does this equation have the option for r to equal 0? Is it possible to plug something in for theta and still get a 0 out of this? Sure. If theta equals 0, then the sign of 0 is 0, and we're okay here. So there's nothing wrong with this equation. It didn't lose any solutions. This is fine. If for some reason with this equation it wouldn't equal 0, we'd have kind of like a piecewise solution. We'd have this as part of our solution, or r equals 0 as part of our solution too. Okay, it doesn't happen a whole lot, but it's worth mentioning there. Russell did go back and say he can kind of see the easier way to go through and do this here. What we did isn't wrong, and there's nothing wrong with doing it that way. But imagine taking this very first equation. If we would add x squared to both sides, okay, what does x squared plus y squared equal? It equals r squared. So you can just say, okay, well, r squared equals 3 times r cosine theta, or sorry, r sine of theta, replacing for the y, and then just again divide through by r and we're done. And if you recognize things like that, then it's a-okay to do them. If you don't, then the way we did here will work every time too. Okay?
Why would we want to divide by r?
Just to write it as simple as we can. Because like you know how usually in function notation you try to get x or y by itself or z by itself, r is kind of the variable you want to try to isolate. So if you can get your equation just be r equals something, then that's better. And so
we still have r on one side. We still have r on both sides.
where? When? What?
So we get r squared equals
Okay.
divided by r.
Right?
Yeah. R squared v sine over r. Oh, never mind, I forgot the r.
Okay,
You're right,
okay,
I forgot the r.
Okay. All right. We will do basically the same exact type of thing, but just with the z in it. So let's. There's no good place. Sorry, buddy. I'll keep moving around. Let's see if it works on there. All right. So cylindrical coordinates. How does this change when we jump up to a third dimension? It really doesn't change much. We literally just put z on the end of it. R means the exact same thing. Theta means the exact same thing, and z means the exact same thing it has before. It's just your height up and down there, which is why we call this cylindrical coordinates. If you think about taking those two-dimensional polar graphs we're making, we said that, remember, a cylinder just means you extend this up in the z direction. So all we're really doing is taking this polar graph and just adding the z component, allowing it to slide up and down there. Okay. Now shapes can get more complicated if z is going to vary, but that's kind of the idea, the reason behind why we call this here. So we are working with ordered triples. There are still just going to be r, theta, z. Again, r means the same exact thing, theta means the same exact thing, and z is just that distance we're going up or down there. So when we're making our conversions between cylindrical coordinates and rectangular coordinates, really it's the same thing we just had. X is still going to equal r cosine theta. Y still equals r sine of theta. And z is just z. So rectangular coordinate z, spherical coordinate, cylindrical coordinate z are the same thing. So on the other half of this, we still have x squared plus y squared equals r squared. We still have the tangent of theta equals y over z. And z just equals z. So again, if you understand the polar coordinates, this really isn't much more work. It's very, very, very similar. Okay. Now, visualizing this, though, once we have to start graphing things and working with this, like physically, may become a bit more difficult here. So back to Math Insights. They do a really good job of explaining kind of what goes on here. So I just searched Math Insights, cylindrical coordinates. Okay, they go through and do some talking. They explain the pieces here, but this is really what I wanted to bring up. It's just part of their website right there. Okay. So x-axis, y-axis, z-axis. We know that this red line here, that's representing the radius. So how far away are we going from the center? And I can adjust that. When we have a small radius, our point is close. When we have a big radius, our point is far away. Okay, we know what that means. It could be negative, and that's fine too. Theta is that angle from the positive x-axis. And so right here, we can see that's shown in green. And we know how this works too. Theta can be big, can be negative. This just kind of goes on part of the range test. So we are comfortable with those two things here. And then really all z is doing is that purple, that height distance there. And again, it's the same thing we had in rectangular coordinates. When z is small, we're on that plane. Z can go below, z can go above, and we're just moving that point around there. Okay, and then you can also drag your point and kind of see how it affects things. But we should be fairly comfortable with this one. All the pieces we've worked with before, it's just kind of combine those two things together there. Okay, so that's cylindrical coordinates. If we're graphing points in cylindrical coordinates, we can convert them from rectangular to that or leave them however you're comfortable with there. But let's go ahead and convert this one and then try sketching a rough plot of it there. Okay. All right, so we are given the point currently in polar coordinates or cylindrical coordinates, and we want to work backwards and we want to get the x, y, and z coordinates. So we need to know what x equals, what y equals, and what z equals. I'm gonna do the easy one. Z is 2, doesn't change. Okay. How are we gonna find out what x is equal to? Right here. So for this problem,
3
r is 3, cosine of pi over 4. And then what is cosine of pi over 4?
Square root 2 over 2.
And so 3 root 2 over 2. Okay. And then similar for y, we're going to have 3 times the sine of pi over 4, which happens to be the same thing. Okay, so the actual point that we're working with is 3 square root of 2 over 2, 3 square root of 2 over 2, 2. So if we try to sketch this guy, there's my plane, my axes, x, y, and z. If you'd rather graph a polar coordinate, that's fine. If you're okay graphing a time coordinate, that's fine. They're going to give us the same point, just different ways of going through and doing this. If we graph this as this rectangular coordinate, oh, what is 3 times square root of 2 over 2 approximate? Excuse me, approximate equals 2. Your calculator handy? Yeah. Be fast in the opening line. You like
2.12. 2.12.
2.12, sorry, I hear you now. Okay, get that same thing. So if we go 1, 2, a little more than that for the x, and then similarly 1, 2, a little more than that for the y, my point's going to be kind of sitting in this plane, but then we have to shift it up 2 units for z. This is when I really, so about over here. Okay, we move this guy up 2 units. I don't know how much that helps. But there we go, there's our point. Okay. If we think about this in the polar coordinates, we've gone out, we are sitting on that 3rd circle, which I'm not going to try drawing here because my picture muddy. But we can see at that angle coming out from the origins at pi over 4, and then we still just go up 2 units there. Okay. Going backwards to cylindrical coordinates, we can just work the other way around there. We've got time, so we'll do it. All right, example 6, we are given x, y, and z in this case. We want to find our theta and z. And again, the easy one is z. What's z going to be equal to?
2.
The same thing. How are we going to find r or theta? And almost same thing, we're working backwards on it, right? So r, there's again, this is where we have multiple ways we can write these answers here. So if we think back up to this, if we want to solve it for r and actually have r by itself, r can be the positive or negative square root of x squared plus y squared. And similarly for theta, if you want to solve this for theta, theta is the arctangent of y over x. Okay. And if you'd rather write it that way up there, go for it. Okay, so as we usually know x plus y equals r squared. It works out nicer for trigonometries too. So either way, for r, we're going to do plus or minus the square root of the x component, which is 1, plus the y component. And I am going to leave that as 2 possible solutions now, and then we'll write our answer together in a minute. So what does that give us? 1 plus 3 square root of 4, so plus or minus 2. Is positive 2 correct or negative 2 correct? Or is 1 wrong? Okay, either one is okay, depending on the angle we pick to go with it there. Okay, so going through and doing a similar thing here. Theta then is the arctangent of y over x, so square root of 3 over 1.
Which is,
I'm not as good at this.
it's,
The pi over 3 or pi over 6, it's one
yeah,
or two
it's
of them.
one of the 2.
I don't think I have a unit circle handy here.
It should be powered. It should be powered through. You got root 3 over 2 divided by 1/2, so 2's will cancel, so it's powered through.
Okay, so pi over 3. We're going to go with Russell. I think he's right. So if we reduce that down, and your calculator can give you approximations. I don't know if the fancy ones actually tell you it's pi over 3, not 6. Sorry. Okay. Again, that's only one solution, right? We know that we can go like the opposite way around that circle and get to that, or we can make another lap and get to that point too. So for example, another possible solution we can have for this would also be negative 5 pi over 3, right? That would bring us to the same angle, just going the other way around the circle to get there. And we can keep going. There's a whole bunch of these points that work here. But the reason I mentioned that is because that kind of makes sense of why we have positive or negative root 2. So if we think about this point here, we've got options for it. So if we pick a positive 2 for the radius. Which angle is more appropriate here, pi over 3 or negative 5 pi over 3? Okay, I'd probably stick with that one too, just because it's nice and easy to work with there. Although if you like negative 5 pi over 3 there, that's okay too. And I kind of was a little deceiving just now there. If we do a negative 2 for the radius, neither of these actually are the angle. What would be the angle if we do a negative 2 for the radius?
The negative 5 pi.
4 pi over 3.
No, it won't be this one. I heard some.
Negative 4 pi.
Not even negative, just positive 4 pi over 3. Okay. So this should be another valid point for that. And don't even worry about the z component right now. Just think about the r and the theta. If we have a radius of 2, so let's draw circles, okay? Pi over 3 is somewhere over here. So there's the point we're talking about. If we do a negative 4 pi over 3, so that would be, oh no, 4 pi over 3. Yeah, so that would go 1, 2, 3, 4 pi over 3 is down here. But then our radius is negative, so we're going to go backwards. So that still takes us to the same point there.
Negative 5 pi over 3.
Yeah, negative 5 pi over 3 is a normal spot, right? Okay. So there's tons of ways you can write these things here. Wolfram, Webaside. Webaside is good about picking up multiple answers there, but just pay attention to the directions. If it asks specifically for a positive angle or something like that, then make sure you tell it that angle. Okay, and then plot the point. Just think about taking this and raising it up to units. I won't bother going through and graphing it in 3D. It just looks messy. All right, but like we said, we already answered this. What's another way we could write the example for number 6 here? Well, that's what we just said. If we think of this as a negative radius, this is the same point. Okay, or if we just think about it as a little positive radius, that negative 5 pi over 3 also takes us to the same point. That would also be okay. I mean, we can write alternate ways of doing this for the rest of forever, and we would never really end. There's an infinite amount of ways we can go through and do this. But I would say having everything positive is probably the most common way of doing it. Just be aware there's other ways you can go through and write this. Okay. All right. Questions so far? So just like sometimes polar coordinates make things a lot simpler. Think about like a circle. A circle in rectangular coordinates has to have an x squared component and a y squared component. A circle in polar coordinates, if it's into the origin, is just r equals a number. So it's a much simpler equation to work with there. And we have a lot of similarities here. So if we're working with some three-dimensional surfaces here, a right cylinder, we've talked a little bit about this, x squared plus y squared equals 9. We know it's a cylinder because we're missing the z component. And so if you think about just the shape that x squared plus y squared equals 9 makes, it's just a circle. And so in cylindrical equations, we still don't have that z component because it could be anything. We're allowed to be anything there, and we're just left in that circle. For a cone, we talked about quadratic surfaces there, x squared plus y squared equals z squared. Well, a cone in spherical coordinates, in cylindrical coordinates is just r equals z. Again, a much simpler equation to work with, and then same thing for a plane. Some of these things are going to simplify down quite nicely. And if you think about what you guys know about integration and derivatives, those simpler equations are much easier to derive and to integrate than the more complicated ones. And that's really why we bother talking about this. Okay, so when we get to the chance we're actually finally talking about doing the calculus with this, sometimes it's going to be a lot easier to use the other surfaces, the other coordinate systems. All right, so let's convert some more of these points here. Find the equation in cylindrical coordinates for the surface represented below. Well, first of all, tell me about this surface. We know it's 3D because we have x, y, and z. Okay, is it a plane?
No.
Why not?
Because the square.
Why is it not a plane?
Okay, it's square.
Yeah, we got squares on there. If it was a plane, it'd have to be linear terms all over the place. Okay, so are all 3 variables squared?
Yes.
Yeah.
Okay, which means hopefully we think back to then it's one of these quadratic surfaces. When all of our variables are squares, it's probably going to match up with one of those. Okay, and we can go through and we can keep working this. Not really what the question asks, so I won't keep going from there. But at least kind of have a little bit of an idea there. Those simple things like working with a plane or a cylindrical surface, hopefully we start to kind of be able to pick up and expect what to see there. But I'm not going to expect you guys on the fly to just be able to tell me it's hyperbola of 2 sheets or something like that. You just know it's a quadratic surface. Because the other thing we can do is we can just graph it, which I will do.
That's fun.
X squared plus y squared. Oh, sorry. We know it's not going to be a paraboloid.
You?
There we go. It is a cone. Okay, so we get a double nap cone on this one. All right, so there is the surface that we are working with, okay? Now, we just said in the table above this that it's easier to write cones in cylindrical coordinates, okay? So we're gonna go through and see that and hopefully get a slightly easier equation to work with there, okay? So again, it is a cone, not nearly necessary to answer this question, but useful to kind of recognize. All right, so really what the question wants to know is how am I gonna take this with X, Y, and Z and rewrite it with R, theta, and Z? I wanna write this in cylindrical coordinates, what can I do?
X squared plus y squared equals 1.
Well, equals r squared, right? Let's do that step first. But yes, what you're saying is the way we do it here. If we recognize this is the same thing as r squared, we can save ourselves some time. So let's do that since we recognize it right now. If you did recognize that, you go back and say, well, x equals r cosine theta, square that. Y equals r sine of theta, square that, and we can proceed as before.
And r equals z.
Yeah, and so we don't have to do anything about the z part, right? I mean, z is still z in polar coordinates and rectangular coordinates. All those things are still the same there. We could almost just end here, but ideally we'd like to try to simplify as much as possible. Luckily, everything is a perfect square in this one. So let's take the square root of all that stuff. So r equals technically the positive or negative square root of 2z.
If you didn't recognize the line test, you just have to go x equals r.
Cosine theta. Yep, and then just do a bunch of it. It's not really much longer to do it that way, but yeah, you know, short to that. Okay. Okay, so before we do this too much, does having a positive and negative here really make a difference?
No.
Yeah, in this case, it's not really going to make a difference here much because z has the option to be positive or negative already. And r, we know, can be positive or negative. So if we just say r equals z, we're going to account for the fact where it's maybe going up above and positive and down below negative there. It's not really going to matter in this one here. There are times where it does make a difference. This is a case where it really isn't going to matter there. We're still going to get both pieces of that cone by dropping that off there. And if you're not sure, leave it there on test or quiz. I'm not going to mark you wrong, because that's not wrong. It's just we can simplify a little more and just get that. I don't know how this does with special. What does that mean? Yeah, I don't know how to graph in cylindrical coordinates in this system. Let me see. Z equals, it'd be 1/4 r then. All right, so this one I just have the top of that cone there, but here's a different program going through and graphing that same surface. And like I said, I'm not going to worry about changing. I didn't input enough information there. I should have told to look for negative values also. But anyway, you can see that there's the cone, there's the cone. We're getting basically the same top piece there. Okay, so we do have the same top. I just didn't graph all of it here. Okay, so there you go, that. All right, example 9, find the equation in cylindrical coordinates, which again means r, theta, and z, for the surface represented by this. What's the graph of this look like? X equals y squared?
Parabola.
Parabola, and which direction is our parabola opening?
The y.
Yeah, it's on along that axis there off to the right. Okay, so we know the graph of this one, and we don't need to pull it up with Desmos. So how am I going to convert this guy to polar coordinates or cylindrical coordinates? Yeah, we're going to have to use the r sine, r cosine piece here. So there's really no shortcuts with this one since we don't have all the pieces for our shortcuts. So remember, r is the same thing as, or I'm sorry, y is the same thing r sine of theta. X is the same thing as r cosine theta. And then we're going to try to simplify this. Okay. Before I get too much further, in 3 dimensions, what does this graph look like? So you're right, it is a parabola, y equals x squared, x equals y squared. But what's it going to look like in 3 dimensions?
Is it going to look like
flat?
It's not quite flat. We're missing a z component though, right? So you're on the right idea. Remember what we said back here about these guys, got cylindrical coordinates? Where we're missing that component, that direction's kind of been stretched in. That's what's happening here. So we've got this on our XY plane, we have this parabola, and we're basically just stretching this thing up. So it's like if you took a sheet of paper and just kind of bent it, and just made kind of like a curved sheet of paper, it's really what we're talking about here. Or like that very first thing, but it's kind of tilted on its side. And again, not imperative to do that. Give me a minute because I'm in class, so. Okay. So, where were we at? Okay, go ahead and distribute r squared sine squared theta equals r cosine theta. Ideally, we'll try to get r by itself. So what can we do here? And if we divide by r, Just make sure we're careful to go back and check about can r still equal 0 at the end. Okay, because if it can't, then we have to add that solution back in. So r sine squared theta equals cosine theta. What we do now, you get r by itself?
Divide by sine squared theta.
Uh-huh. And I would be okay if you left it like this on a test or quiz, that is fine. But what the homework is going to expect you to do is write that not as a ratio. So if we think about cosine over sine, what trig function does that equal?
Tangent.
Cotangent.
And
Cotangent squared theta.
We'll have cotangent theta, and then 1 over sine is cosecant theta. So that's probably a better way to go through and write this one. All right, equals r there. Yeah, it is pretty good about that. That's why it surprised me on Reddit that it didn't recognize the squared.
Yeah. Maybe I wrote it.
It's probably just as programming thing. It's probably not you. Can r still equal 0 with this one? So like, can cotangent of theta equal 0 at some point? Pretty sure it can.
yeah,
And the same, or cosecant. As long as one of those guys is still going to give you 0, we're good there. So we didn't lose anything with this. That's still okay. So there we go. That's our solution.
so what, let's just say they couldn't work, what would we do?
We'd have to have like a multi-part equation there. We'd say, okay, and there's really no pretty way to write this, but basically piecewise, you'd have r equals 0 if something, something, and then the rest of it with the rest of it there. But that probably won't come up with problems we work with.
Gotcha.
So even though there's really no benefit for us to check in, it's still useful mathematically just to make sure we're aware of that. Okay. Let's do the last one, and then tomorrow, we won't talk about tomorrow. Monday, we'll talk, Tuesday. We don't have class on Monday. Tuesday, we'll finish this up. Okay, find the equation, rectangular coordinates for the surface presented by this. So now we're going to go from our r theta z to x, y, and z. So working backwards from what we did before. This one's a bit trickier. So I'll first open up for suggestions. Any suggestions from you guys?
Z squared equals r squared. Well, whatever increases, z squared is the same.
Yeah, z squared isn't going to change, so we're still going to have a z squared. Also, that plus 1 isn't going to change. It's just a constant. So really the question becomes, what are we going to do about this guy? Is there any obvious thing we can do?
Cosine 2 theta is half angle identity.
Yes, we can use our trig identities for this one. Okay. So let's first try to just rewrite this. And I don't know the names of the identities, I'm not going to lie. I know they exist, but I'm not good at names. But I do know that this one is the same thing as the cosine squared of
I think
theta
it's double I.
minus sine squared. Is it the same one you were thinking about, Edwin?
Yes, ma'am.
Okay. So yeah, if we recognize that from that cosine of 2 theta, there's really nothing we can do with that because all of the conversions we have are just based on cosine squared or sine squared, but just working with single angles, not multiple angles. So let's get rid of that multiple angle. Okay. And then from here it's a little bit easier. Okay. Distribute that r squared. Plus z squared plus 1 equals 0. And now hopefully part of that looks familiar. Can we do any conversions now?
Factor out an r.
We could factor out an r, but let's not do that. Is there a better thing to do?
No, yeah, that's right.
Oh, we can make them at x1.
Yeah, so now we know that x equals r cosine theta, so x squared is r squared cosine squared theta. So this term right here is just x squared. This term right here, this is just y squared. And then we still have that z squared equals, or plus 1. And now we are rectangular coordinates, okay? You can stop there, that is fine. But if we did a little bit more work on this one actually turns out to be a hyperboloid of 2 sheets. So let's real quick just rewrite this. So if we subtract 1 from both sides, and then we don't like to have a constant, a negative 1. We want the constant to be a positive 1 for our quadratic surfaces. So divide everything through by that negative 1. And so we have negative x squared plus y squared minus z squared equals 1. And this just looks more like a hyperboloid of 2 sheets. That step is necessary. If you left it right here, you're A-okay. But just match it up to what we did before. That's what this would be. Okay? All right, so polar coordinates. If you were resting on polar coordinates, then maybe go back and review through your notes, or this may be enough of a review there. I'll get the homework posted for this pretty soon, so you can try starting on that. But when we come back on Monday, we have no class for Labor Day. Tuesday, we'll finish up this section. We have one more coordinate system to talk about there, and then review on Wednesday, whatever it says in the calendar here. Okay, so this will be still more of the chapter. We won't do chapter 12 yet, then we'll start chapter 12 on Thursday. But tests next week will be available Wednesday, Thursday, or Friday. So for you guys, the
How many
testing
questions
here.
are there on your exams?
One more time.
How many questions are there on your exams?
15 to 20. Last year, my chapter 11 test had 15 questions. One of them had multiple parts, so 15, 16, 17 total questions there. As far as how much time you should need to take it, we were talking about this the other day with the guys here. I had a student last semester who took a really long time to take things, like much longer than he probably should have. And it took him 2 hours and 45 minutes to take this test, which was a really long time there. Almost all the other students finished between an hour and a half. So if you're a long test taker, give yourself more time. But if you finish that average, if you give yourself an hour and a half, you should be good for this one there. Okay, but plan accordingly. You guys know yourselves better than I know you at this point.
Are we doing the note card thing like we did?
One more time?
Are we doing the note card like we did Calc 2?
Yes, I will let you have a note card. You can write whatever you want on there. So I was going to say is Tuesday, I'll try to have the review sheet so you guys can start working on it there. That we're still going to material. And yeah, you can have a note card. You can write whatever you want on it, front and back. I don't care. It's just for you guys. And you can use the fancy calculators too. So if you want to use the 89s, that's okay. I'm still going to want you to show your work. And yes, I know there's ways you can get around that, but I still want you to show your work. So use it to like help check, help graph, and things like that. Okay?
We want to show our work on cross products.
Say that again. I didn't hear you.
We want to show our work on cross products, or can we use our calculators?
I will probably ask you to show your work at least once on cross products, but then if you have to use it within a problem, you can use your calculator. So I want to see that you can go through and do it, but doing it every time is lengthy. So like I said, demonstrate it once, I'll check your work, and then if you use it within a problem, you can use your calculator.
Cool.
Okay? All right, if you guys have any other questions, let me know. I'll try to get that stuff from Lisa figured out today for those of you that's not working for. But at least you've got that access through finish this homework so we can deal with it next week if I don't get it taken care of. Okay?
Could you look at my picture and tell me what I'm doing wrong?
Yeah, I'll go back and check that one. I'll do that now before I leave for lunch. I'll go back and take a look at that. Okay? All right, have a good weekend, guys.
See ya.
Yeah.
Thank you.
All right.